All right, greetings everyone. Welcome to our first video for section 4.6. Wait, what? We were just doing chapter 2. Why are we in 4.6? Well, you will see here in a minute. I also want you guys to know I'm very proud of this meme that you see here. As we're recording this, we're of course in the middle of the coronavirus pandemic, so I thought that a meme about things not touching might be hilarious. Okay. So as I mentioned, we are jumping ahead in our book to section 4.6. We will go back to actually chapter 3 after this, but section 4.6 contains some information about limits at infinity, which do relate to asymptotes. So that is why we are looking at this. Okay, so the first thing I want to do is look at graphs of some functions to determine the limits as x approaches positive infinity and as x approaches negative infinity. And if you remember from pre-calc 1, wherever you took that, when we're talking about what happens as x goes to positive or negative infinity, or really as our inputs go to positive or negative infinity, we're looking at something called long-run behavior. So we really want to know what is the long-run behavior of each of these functions. So to determine this, we're going to use our calculators. So we're going to do some graphing here. So I've got this set up here. I'm going to go into my y equals. I'm going to graph that first one. So negative 13x squared plus 27x to the third. Okay, so our function looks like that. If we graph that, we get a picture looking like this. And so we want to look at what happens as x goes towards positive infinity and as x goes towards negative infinity. And we're looking at what happens at the outputs, right? So as x goes towards positive infinity, what do we see the outputs going towards? Well, we're looking at the graph as it goes this way, right? Because that's what happens as the inputs increase, and it looks like the outputs are going towards positive infinity, right? The graph is shooting up. As x goes towards negative infinity, what are our outputs doing? Well, here it looks like the graph now is diving as we go this way. So it looks like the f of x's this time are going towards negative infinity. So this is one of those examples of where we see the tails going in different directions, right? Okay, so that's one possibility for what we might see. Let's look at another. So the second function we had there was x squared minus 1 over x squared plus 1. So we'll go ahead and put that into the calculator. Remember, when you're doing this function, you need to be very careful about parentheses. So we'll do x squared minus 1 divided by x squared plus 1. And as I was saying, be careful about parentheses. I, of course, forgot a set here. X squared plus 1. Okay, there we go. We'll graph this. So we get a function that looks like that. Let's now look at what happens again as x goes towards, the inputs go towards positive infinity, and as the inputs go towards negative infinity. Okay, well, as we go towards positive infinity, we're looking at what happens to the graph as we go this way, right? And it looks like the graph is kind of flattening out, but it's hard to tell. So one way to get some certainty is if we press second graph to go to the table and start increasing the input values here and see what we see. And it looks like we're getting like 0.998, 0.999, things along those lines. So what do you suppose that the outputs are approaching there? Right, it looks like they're getting closer and closer to 1, right? So as x goes towards positive infinity, it looks like our outputs here, which our function is called g of x, the g of x values are getting closer and closer to 1. Okay? Now what if we go the other way? So going back to the graph, what happens as we go towards negative infinity now? This way. Okay, well, we can go back to the table here, and let me just, I guess I can do this. Gotta go all the way back to 0. And then as we go in the other direction, towards negative infinity, looks like we see something similar to what was happening before, right? So it looks like our output values, our g of x values here, are getting closer and closer to 1 as well. So here was an example of where we saw that the output values, or the kind of limits in each direction, were exactly the same, right? We had the same thing. Okay, and then our last one is, we're looking at 1 over x as our function. And what do we notice here? This one seems a little bit clearer. So as the input values go towards positive infinity, what does it look like the output values are going towards? You guys are right, they're going towards 0. And then as we go towards negative infinity, yes, I agree. It looks like they're going towards 0 again. Okay, so this is another one we see in each direction. The outputs are getting closer and closer to 0. Now, an interesting thing about this is using the function just 1 over x, right? But what if we increase the exponent on the x? So let's say it's like to the 2nd power. Let's see, does that change the long run behavior? Well, it kind of changed how the graph looked, but notice that as we go to the left and to the right, it still looks like the outputs are getting closer and closer to 0, right? What if I try another higher exponent? So what if I do something like, say, 1 over x to the 5th? Well, it still looks like we see that same pattern, right? It's going towards 0 in each direction. Let's try one more. Let's say we do 1 over x to, say, the 75th power. So the picture of the graph has changed a little bit, but notice it still is going towards 0 in each direction. Okay? And that one is really significant to us because, if I go back to my PowerPoint here, we can generalize that and use that as a theorem. So we're told here that if r, which is greater than 0, so it can't be a negative number or 0, is a rational number, then the limit as x approaches infinity of 1 over x to the r, okay, so this is like a rational function where we just have a single variable raised to a power in the bottom. Well, as x goes towards positive infinity, that will always be equal to, that will always be equal to 0 is what this is telling us. Okay. Similarly, if we have a similar setup where it's 1 over x to the r, but we're going towards negative infinity this time, well, still the limit will go towards 0. Okay. And before I go on to the next thing, there was one more thing I forgot to say at the beginning of this section. So up until this point, we've been looking at limits approaching particular values, right? We looked to say the limit as x approaches 2, or as the limit as x approaches negative 3. Now we're generalizing a little bit more and looking at what happens as the input values get really, really big, so they go towards positive infinity, or really, really small, they go towards negative infinity. Okay, so let's look at finding limits algebraically using those theorems we were just talking about. And we're going to start with the one on the left there. And there's a couple of different ways to approach this. So one way, if you remember from Math 141, from pre-calc or wherever you took that, when we're looking at a limit or long-run behavior towards, as x goes towards positive infinity, one way to figure that out is to look at the ratio of the leading terms. So by the leading terms, I mean the terms in both the numerator and denominator of our function here that have the highest power. So we see here that we have one negative x squared on the top and x cubed on the bottom. So if we have negative x squared over x cubed, notice that reduces to negative 1 over x. And that 1 over x thing we saw here, that's what we were just looking at. The limit as x goes to infinity there is just going to give us 0. So this one would be one where the limit is 0. Okay, but I want to look at a different approach to this. One that's used a little bit more commonly. So I'm going to start by rewriting the limit. The limit as x approaches infinity. And then in my denominator, I want to identify what is my highest power. Well, here I see that it's an x cubed. So what I'm going to do now is something that's going to seem a little strange. But I'm going to go through and every term in this function I'm going to divide by x cubed. So I'm going to do on the top, I'm going to do 1 over x cubed minus x squared over x cubed, and then x cubed over x cubed minus x over x cubed plus 1 over x cubed. Okay? Now that's legal because I did it to everything, so it doesn't change the value of the function in the expression here. And what I'm going to do now then is do some reducing. So this is now be the limit as x approaches infinity of, we'll still have the 1 over x cubed, that's not going to reduce any. The x squared over x cubed looks similar to what we were just doing. That'll become 1 over x. Over x cubed over x cubed becomes 1, minus the x over x cubed will be 1 over x squared. And then the 1 over x cubed stays the same. All right. Now, if we wanted to get really fancy from here, and mostly if I had more room on my PowerPoint slide here, if you remember from our limit laws back in section, I believe that was 2.3, we saw that from here, when we have a limit of two things being divided, we could take that and make it just take the limit and put it to the top and then do a limit of the bottom, right? And on the top, we have the limit of something minus something, so we could break that into the limit of the first thing minus the limit of the second thing and evaluate those. And then we could do a similar thing on the bottom, break this into the limit of 1 minus the limit of 1 over x squared plus the limit of 1 over x cubed. Okay, if we wanted to break it down step by step. Now, we're not going to do that right now, but let's imagine that we did and think about what each of these limits will be equal to. So if we did the limit of 1 over x cubed as x approaches infinity. Well, based on what we just saw on the last slide, that's going to be 0. Minus, we do the limit of 1 over x. Again, that will be 0. All over here on the bottom, we'd be doing the limit of just 1. But if you remember, if we take the limit of a constant, it's just that number, so we'd have 1. Minus the limit of 1 over x squared. Again, using the thing from the last slide makes 0. And then plus the limit of 1 over x cubed also makes 0. And you'll see we end up with 0 over 1, which is just 0, which is what we had before, right? So aren't you really glad we did this longer way of getting the same answer? I bet you are. Okay, so the limit for that first one would just be equal to 0. Okay, I want to use a similar approach on the second one then. So we have the limit as x approaches infinity. We have 3x minus 2 over 2x plus 1. Again, I'm going to identify the term on the bottom that has the highest power of the variable, which in this case would be the 2x. And I'm actually just going to look at what the variable with the highest power is. So that's just x. So I'm going to go through and divide everything in this expression here by x. So this would become 3x over x minus 2 over x over 2x over x plus 1 over x. Okay. Do some reducing here. So we have the limit as x approaches infinity of 3 when the x's cancel out, minus 2 over x over the 2 x's will cancel here, so we'll just have 2 plus 1 over x. Then we again, using our limit laws, think about taking the limits of each of these individually. So the limit as x goes to infinity of just 3, well, that's a constant, so that'll give us 3. Minus, now the limit of 2 over x, well, remember when we have a constant like this with the 2, we can pull that out the front of the limit. So do a little scratch work here. So this would be 2 times the limit as x goes to infinity. If we take the 2 out, you'll see that just becomes 1 over x. And so notice this part right here is the limit as x goes to infinity of just 1 over x, which would be 0. You multiply that by 2, we're just going to end up with 0. So here we have 3 minus 0. Oops, sorry about that. Okay, over, we do the limit of just 2, that's going to be 2, plus the limit of 1 over x, which just gives us 0. And if we simplify that, we end up with our limit being just 3/2. All right, so that will be what that one is. And just to point out another way we could have approached this one, that some of you may be thinking about right now, if we again look at just the ratio of the leading terms there, sorry about that. Okay, just the ratio of the leading terms, we would have 3x over 2x, which when we cancel out the x's, we again end up with just that 3/2. So that's another way to approach that. Okay. Now I do want us to know how to do the other method though, because that's going to come up in more stuff that we do later on in section 4.6. Okay, thank you guys for watching.